In this video, we're going to look at a negative feedback voltage regulator, and specifically, we're going to be using an op-amp to provide the negative feedback control circuitry. First, let's look back at a series regulator that we designed in a previous video and review its shortcomings. A simple series regulator uses a zener diode to provide a reference voltage at the base of a transistor. If it's a silicon transistor, we know that the base emitter junction voltage drop is going to be approximately 0.7 volts. This means that the load voltage is going to be almost constant. It's just the zener diode voltage minus 0.7 volts. But there was a problem or a shortcoming with that regulator. The shortcoming is that we can't assume that the base emitter voltage is going to be constant with the emitter current. That would be this model. That's not what happens in reality, though. In reality, it behaves like a diode, and there's an exponential dependence of the emitter current on the base emitter junction voltage. The effect on our regulator is going to be the following. As the load resistor changes, the amount of current passing through it is also necessarily going to change. But because the current is changing, then the base emitter voltage of the transistor is also going to change, which then changes the voltage supplied at the load. That's what we're going to solve in this video. We're going to be using negative feedback as shown in this diagram. Now, when you first look at this diagram, you might see a lot of different things, but it turns out that the circuit ultimately isn't too bad. The key to this circuit is the error amplifier. It's basically a comparator. It compares the voltage that we actually have to the voltage that we want to have. Here on the left side, I have a box called reference voltage, so that can be provided by a zener diode. We're going to compare the voltage provided by the reference to some fraction of the load voltage. Since we have a simple voltage divider here, we can set up whatever ratio we want. If these two voltages are the same, then everything's perfect. However, if there's a difference between these two voltages, we want to amplify that difference a little bit and provide a corrective current that adjusts the base emitter voltage accordingly. Resistors R1 and R2 are simply a voltage divider. They are going to draw some current from the load side of the circuit. We obviously don't want that current to be very high. This means that the values that you choose for resistors R1 and R2 need to be fairly large. So we're looking at large resistors here. K here is just a ratio. It's the voltage divider ratio. The other thing to keep in mind about this circuit in general is that we don't want the transistor to saturate. The collector-emitter voltage of this bipolar transistor is just the input voltage minus the output voltage. In order to keep that transistor from saturating, I recommend that you keep at least a 2-volt difference between the input and output side. In other words, if you're going to design a voltage regulator that supplies, say, 10 volts at the output, I recommend that you target a 12-volt or higher voltage at the input side. Let's now look at an implementation of this circuit, and I'll explain it again. I think you'll get the hang of it. First of all, we have our reference voltage. That's provided by the zener diode. The zener diode operates in breakdown mode, and this voltage tends to be fairly stable. V sub R denotes our reference voltage. Choosing the zener diode effectively programs the entire circuit. Let me write the word fixed just next to V sub R to indicate that that voltage doesn't really change. What the op-amp does is it compares our fixed reference voltage to some fraction of our actual output voltage. Because of the negative feedback loop, this op-amp tries to maintain equal voltages at the two input pins. That is, the op-amp forces the reference voltage V sub R to equal K times our load voltage V sub L. As I mentioned before, K is just a ratio. It's a voltage divider. Let's think about two different situations. What happens if our load voltage is a little bit too high, and then what happens if our load voltage is a little bit too low? If our load voltage is too high, it means that this fraction of it is also too high. Since this line is connected to the inverting pin of the op-amp is going to lower down the voltage very slightly at the output. This will lower down our voltage at the emitter. It's no longer too high. In other words, the negative feedback loop serves to fix the problem. Now let's consider what happens if the load voltage is too low. If the load voltage is too low, some fraction of the load voltage is also going to be too low with respect to our reference voltage. When the op-amp subtracts these two voltages, it's going to get a positive number. Since it gets a positive number, this voltage will increase a little bit. Passing through the emitter of this transistor, our load voltage, which was previously too low, is going to increase a little bit. In other words, the negative feedback loop set up by that op-amp is going to fix the problem. The only thing that we really have to keep in mind when designing this kind of voltage regulator is to not choose resistors that are too low, and we also need to make sure that not too much current passes through our zener diode. The situation is actually better than the situation of our series voltage regulator because this op-amp doesn't need very much current at all. That means that we don't need very much current passing through this resistor, and the zener diode doesn't need to have a lot of current flowing through it. In summary, the use of negative feedback is able to solve the primary problem with the series regulator that we looked at before. The only other thing that you might want to do to make the circuit a little bit better would be to add capacitors both at the input and the output side in order to stabilize the voltage a little bit.